Hello everyone, I'm Alex from National University of Singapore, and today the topic of my presentation is bedrock detection based on seismic interferometry using ambient noise in Singapore, and co-also include Dr. Enhedelihai from National University of Singapore and Dr. Karen from Nanyang Technological University.
In the first part, I will introduce the objective of our work. Singapore is a very small city but has a very dense population, around 5 million people. It is a very big city, and among the limited human habitable area, around 23% are reclaimed area. Due to this lack of space above ground, making better use of underground space is more essential for the metro city like Singapore. So what is happening in underground in Singapore? In the shallower part, we have different kinds of pipes and tunnels for both water and fibers. And from 15 to 50 meter, we have MRT system and major roads. And for the deeper area, we have deep sewage system and underground storage facilities. So there's a lot of things going on in Singapore, and they both moving toward underground. And for underground construction, the civil engineers has particular need of mapping out the bedrock depths. The need is actually for two aspects. One is for shallow bedrock that is between 20 to 50 meters for construction purposes, and for storage purposes, the deep bedrock of mapping out is around 100 to 300 meter deep. Besides that, the resolution should be really high for these purposes, and the errors that can be tolerated for civil engineers is really small. And besides, as Singapore is a very populated area and we don't have much space to operate the observation, so how to conduct an acquisition in that already built limited area is a big problem. The acquisition is limited and the survey line cannot be too big. And we are also restricted to use any exclusive method. So how to get this high resolution bedrock map would be a big problem. The most conventional way of site investigation is drilling boreholes, just like the figure. Drilling into the formation and takes cores out, and then they will know the bedrock depths. And the drawback is we can only get the formation structure in that particular point, and drilling itself is very time consuming and expensive. And also, just like the right figure shows, the CPT, which is known as cone penetrating test, is also being used to identify the soil type. In this test, a cone penetrometer is pushed into the ground at a standard rate, and data are recorded at regular intervals during penetration. CPT is relatively cheap and fast compared to drilling a borehole, but still, it can only provide us information at some particular point. Besides, the shear wave velocity from boreholes and CPT is not that reliable. And that is why people start to pay more attention to geophysical method nowadays, which is fast, cheap, and can provide us the information of the whole area. So we want to use ambient noise imaging based on seismic interferometry to construct the velocity map of Singapore. It would be non-destructive and can provide us the information of the whole island. And in the next part, I will introduce the geological background and field data collection. Singapore Island is composed of three distinct geological formations. The first one is Jurong Formation in the south and southwest, and the Bukit Timah Formation in the central part, and the old alluvial formation of quaternary sediments in the east. An area of faults and fractures are developed in Singapore, and they control bedrock unit distribution. The Bukit Timah Formation underlies the old alluvium in the east. However, the Bukit Timah Fault is the significant fault that separates the Jurong Formation and the Bukit Timah Formation. And the depth to bedrock is believed to be 50 meters or less for the Jurong and the Bukit Timah Formation, and 100 or more in the old alluvium formation. And for the bedrock detection, we use two sets of data to record the ambient noise. The first one is short period seismometers for the whole island observation. We will use 1 month's data to get the velocity map of the whole island. And another one is the multi-channel observation. It is a short time observation in some particular sites in the eastern part. Continuous seismic records were collected from 81 short period 3-component DLAN nodes. Zealand node is like this. The node has two horizontal components, which is E and N component, and one vertical component, which is Z component. The nodes are set across Singapore, and the location of the nodes are remarked as the blue triangle. Most previous ambient noise tomography work concentrated on period higher than 5 seconds, and they want to get the shear wave velocity of 10 km or more. But in our work, we want to focus on structures within 1 kilometer, which is more related to engineering purposes. If we plot the ray paths along each two stations, we will find our interstation distance is relatively short, so it is possible to use a relatively high frequency in ambient noise tomography. We can also see in the eastern part, we have insufficient ray coverage, so we will deploy multi-channel arrays in that point to get the shear velocity in those particular sites. We have conducted 6 different sites for the multi-channel observation in the eastern Singapore. We want to map out the bedrock depth in this area. In the both of the sites, for getting a real wave velocity rather than an apparent velocity, we set our array as perpendicular to the main road and the coastal lines, which are our main sources. We both using 4.5 Hz vertical component 04 for the observation, and the observation time for positive data is 100 minutes or more. We also observe some active data in the same site to compare the passive and active records. And the site location is remarked as the red stars. The most essential step in our processing is seismic interferometry. By turning a receiver to a virtual source, we can get signal from the noise. If you take the traffic as the source and denote it as RS, then the wave field propagated to the survey line can be seen as a plane wave. The wave field received at receiver 1 and the receiver N can be expressed in this way. And this is the ambient noise record from 24 receivers. And we retrieve Green's function by cross-correlating recorded ambient noise within the chosen time window in frequency domain, and then the cross-correlogram of all short windows are stacked together to improve the signal-to-noise ratio of the estimated Green's function. And it is the final record we have get from the seismic interferometry. We can see we can extract signal from the ambient noise. And in the next part, I will introduce the data processing of short period seismometers. For the short period seismometers record, we cross-correlate all the receiver signal with each other, and finally get a total of 3,214 station pairs. We define signal-to-noise ratio as the ratio between the maximum amplitude and average amplitude for each noise correlation functions. We plot all the cross-correlation functions with a signal-to-noise ratio higher than 20 and rearrange them by interstation distance. The final step noise correlation functions in the period between 0.5 to 2 seconds and 2 seconds to 5 seconds show a clear Rayleigh wave packet travels in the velocity between 0.5 km per second to 4 km per second. From the table, we can find the energy in the band of 0.5 to 5 seconds has the strongest signal-to-noise ratio, can provide us lower frequency information and provide us information from the deeper structure. Then we use frequency time analysis technique to extract group velocity from the noise correlation function from each two station pairs. Basically, for each period of interest, we use a period-dependent window between certain group velocity to window the empirical Green function in the time domain. Then windowed empirical Green function for that period of interest is narrow bandpass filter, and we can get the dispersion matrix by picking up the maximum amplitude in this dispersion matrix. The group velocity from all the stations is like this. Those group velocity dispersion curve from the data will be used in the tomography in the next part. And then we will introduce the data processing of multi-offset arrays. Unlike the processing of short period seismometers record, in the multi-channel arrays, we will set one trace as a virtual source and cross-correlate all the other receivers' data with that one particular receiver. By the standard bandpass filter from 1 to 50 Hz, normalization and spectral widening, we cut the time domain data into a lot of small segments of data and cross-correlate with one trace. After stacking all the small segments of cross-correlated data together, Empirical Green's function on multi-channel arrays can be achieved. In the cross-correlated results of the ambient noise data, the most of the energy is coming from radio wave, and it has a very strong dispersion features. The lower frequency part travels faster than the higher frequency ones. But still, we can find some body wave travels in a very high velocity in a very high frequency range. In the short period seismometers data, the noise sources are believed to be random distributed. But in the multi-channel array, the main source has a certain azimuth. In spite of we try to put our survey line perpendicular to our main source, but the azimuth still exists. In the equation, theta is the angle between survey line and the main source. And the angle impacts the phase velocity strongly, and an azimuth fluctuation of 5 degrees can change the phase velocity in the change of 15%. For correcting the azimuth angle, we compare the dispersion energy matrix of active source data with passive source data in the range between 6 to 10 Hz, and we can get the azimuth angle for correction. In this example, after correction, the phase velocity of passive data can match very well with the active ones, especially in the high frequency range. So passive data can provide a more accurate low frequency information. So after correction, we can get a much more stable and much more reliable phase velocity from multi-channel arrays. After transforming time-space domain into frequency velocity domain, and after azimuth correction, we can get the dispersion matrix of the surface wave. By picking up the maximum energy, we can get the dispersion curve of multi-channel array. Those dispersion curves can be used in the 1D inversion of multi-channel array in particular size. And in the next part, I will introduce radio wave tomography result from short period seismometers. For testing the group velocity tomography resolution in both horizontal and vertical direction, we construct a 3D checkerboard model with a grid of 0.05 degree times 0.03 degree in horizontal and 150 meters in vertical. It has the same source receiver distribution as in the real data distribution. And we also add 3% random noise to the synthetic data. And from the test, we can see the tomography result can clarify this resolution of 0.05 degree times 0.03 degree and 150 meters in vertical direction. From the real data inversion, we can notice the central part of Singapore appears as a high shear wave velocity due to the shallow granite bedrock. Bukit Timah Falls zone appears as a local low-speed anomaly. Low shear wave velocity also appears in the eastern part, which are dominated by quaternary sediments in the shallow subsurface. From the vertical slides, we can also see in the area of falls and quaternary sediments, it has the lowest velocity. And we can notice the velocity is becoming more and more low from west to east. It means the bedrock depth is becoming more and more deep. But due to the source of tomography at a relatively low frequency band, we cannot get a very detailed structure in the shallow part. Additionally, in eastern Singapore, we have insufficient ray coverage to cover the whole old Olivine formation. So we need additionally MASW analysis in the part. The next part, I will introduce 1D inversion result from multi-channel arrays in the eastern part of Singapore. We get the 1D inversion result from multi-channel arrays in 6 sites using a PSO-based dispersion curve inversion. When the velocity is larger than 2,000 meters per second, we can identify the layer as bedrock. From the inversion, we can notice that in the most of the sites, the bedrock depth is 100 meters or more. Compared to other parts of Singapore, the bedrock depth in this part is really deep. For validating the inversion results, we apply the sensitivity test to different sites. Sensitivity kernel can be defined to be partial derivative of objective function to different parameters. And by testing the sensitivity, you can get the influence of different parameters in different layers for the dispersion curve. It can be simply obtained through percentage changes rather than partial derivatives. For getting a more accurate sensitivity result, we apply the analytical solution of sensitivity rather than the numerical results.
The analytical solution of sensitivity can be expressed in these equations. For this slide, we did the sensitivity test to different parameters, such as Vs, Vp, and density. And we can see the impact of Vs on dispersion curve is much more stronger than other two parameters. And in the later part, we will only discuss the impact of Vs for different inversion results. Here is a sensitivity test of 6 sites. From the sensitivity test, we can show in the most of the times, the shallower structures influence the high frequency part of the dispersion curve dramatically, and the deeper structures impact lower frequency part of the dispersion curve dramatically. If the inversion layer at certain depths has no impact on the dispersion curve, but the inversion result in that layer is not that reliable. For example, in the site 1, the layer at 150 meters has a little impact on the dispersion curve, so the inversion result in that layer is not that reliable. We can only trust on the layers that can impact the dispersion curve. And for all the 6 sites, we have bedrock depths from boreholes, inverted bedrock depths, and reliable depths from sensitivity analysis. We compare the bedrock depths with those boreholes nearby, and the depths can change very dramatically. Compared to bedrock depths we get from tomography result, the basic trend is the bedrock depths is relatively shallow in both south and north coastal area, and the depths in the north inland area are relatively deeper than the south part. And the last part is conclusions. Firstly, we use the surface field tomography on a period of 0.5 to 5 seconds, and we can get a 3D shear wave velocity map of Singapore. And secondly, bedrock investigation can be achieved using multi-channel passive sensing survey in an urban environment like Singapore. And thirdly, from central to eastern part of Singapore, the bedrock depth is becoming more and more deep according to our tomography result and multi-channel passive sensing results. And this is all of my talk, and thanks again for your attention.